Right. So we've been going in the last few weeks through some technical material, which I think I've been calling core computability theory. So that's the computability theory about sets of natural numbers and classifying them according to their computability theoretical properties. Are they very nice sets, like decidable ones, and computable sets, or sets that we can only positively affirm the membership of, but not negatively? So those are semi-decidable sets or computably enumerable sets. And that sort of question. So today's going to be the last lecture on core computability theory. Functions of the natural numbers, sets of natural numbers on core computability theory. It's quite abstract material. And then, starting next week, we're going to have a block of 3 lectures, which will take us just up until Christmas, which is going to be 3 lectures on rather than computability with words, finite words, and natural numbers, which you might call computability with discrete data. We're going to talk about computability with continuous data, like real numbers. So the next week, I think today is the 9th lecture. Yeah, I'm sure it's the 9th lecture. So the next 3 weeks, lectures 10 to 12, going to be computability with continuous data. So don't worry too much if you feel that you've seen quite enough of the SMN theorem, for example. I mean, we are going to have to use the SMN theorem again today, but it will not play much of a role in the 3 lectures starting from next week. And indeed, next week it's going to be very much going back to basics, and then we're going to return to Turing machines. So just a little, what's the word for a trailer for next week. In particular, lecture 10 going to return to Turing machines. Of course, by lecture 3 or 4, you're probably thinking you never wanted to see another Turing machine as well. But, anyway, we're going to go back to Turing machines, and it's going to be a different kind of Turing machine from the one. First class, of course, these are called type 2 Turing machines. We're dealing with type 1 Turing machines and but anyway, that's all material for down the line. Today, what we're going to do is finish the abstract material on core computability theory, and we're going to extend our classification of sets that currently we know we've got. Computable sets, the decidable ones, computably enumerable sets, that's the semi-decidable ones, and the only other kind of set we know about is a set that's neither computably enumerable. Well, I was going to say neither computably enumerable nor computable, but of course, if it's not computably enumerable, then it can't be computable. So we're going to see that there are interesting divisions in the world of sets that are not computably enumerable, and moreover, there are interesting applications of those things. And the way that today's lecture is going to be, it's going to be, as always, in 3 parts. The first part is going to be technical on a kind of set that's not computably enumerable, and the third part is going to be technical on another kind of set that's not computably enumerable. And the middle part is going to be quite high level, and it's going to be an application of material in the first part. It's going to be more a narrative-based. So it's a narrative-based part. So hopefully it should be also of interest to people that don't want to think in lectures too much about technical details all the time. Anyway, so the topic today is varieties non-computable set, to make the first variety, we're going to think about sets that are not computably enumerable. So it's very easy to see that the following are equivalent. Observe that the following are equivalent for a set. And of course, in our core computability theory, we're dealing with functions on numbers and sets of natural numbers. So we talk about sets of natural numbers. So it's the same thing to say a set is not computably enumerable. A is not computably enumerable. It's a more complicated way of saying the same thing is whenever we have a computably enumerable subset of A, then we can, well, of course, that computably enumerable subset cannot be the whole set, because if it were, the set would be computably enumerable. So what we can do, because it's not the whole set, we can find some element, little a, of the set A that's outside the computably enumerable subset. So for any computably enumerable subset of A, remember we can enumerate, we've got our enumeration as domains of computable partial functions, the W enumeration of computably enumerable subsets. So this is saying any computably enumerable subset of A, there exists some number in A that's outside of WB. There exists some n in A that's not in WB. Okay. That's it. It's triviality that these two are equivalent. However, what we might ask is, are there interesting circumstances that we can find this element n from this index E? That is, we can compute it. So can a set be computably enumerable in, let's say, a sufficiently constructed, sorry, not computably enumerable. Can the set be not computably enumerable in a kind of positive way that we have a computable function that witnesses that fact, and we have a computable function that will map any index E for a computably enumerable subset of A to an element n belongs to A that's outside of WB. And subsets are very interesting, and we're going to see in the second part some particularly interesting example of such a set. But to begin with, in this property, other examples get a feeling for the concept. And we're going to give it a name, and such sets are called productive. So a set A numbers is productive if there exists a computable function on natural numbers computable total function G on natural numbers such that for all indices E, which we think of as ranging over computably enumerable sets, given in the W sub E enumeration, if W sub E, so for those indices E that are subsets of A, it always holds that G of P is an element of A that's outside of WB. Okay, and this terminology is not in the notes, but I'm going to call this function g an outsider finder because it finds an element outside of WE, in A outside of WE. So we call, this is not standard terminology. It's just useful to have some terminology for it. We call G an outsider finder. Just a remark, there's kind of no real reason here, it seems, in the definition to assume that G is a total computable total function, because we could just require it to be defined on those E that represent subsets of A. However, if we dropped the requirement of totality here, we would get a weaker notion of productive set. I don't know if that's an interesting notion. Certainly, all the literature on productive sets is about this stronger notion, and probably this stronger, the requirement that G is total is needed, I think, to make most of the results. So we're going to, although the kind of concept of being productive and being able to find an outsider doesn't in itself require totality, in order to have a nice definition that has good properties, it does seem useful to have this function being total. In any case, that's the classic definition of productive set. Okay, so observation, proposition, that I'm not going to prove it because it's trivial. Every productive set is not computably enumerable. We'll see right at the end of the lecture that there are computably enumerable sets that are not. There are sets that are not computably enumerable that are not productive. So it's so being productive is, as we will find out right at the end of the lecture, is strictly stronger property than being computably enumerable, but it is being computably enumerable. It is being not computably enumerable in this kind of nice constructive way that we have a computable function that will find outsiders. Okay. And before going on, just something else that's not in the notes. And these are just, I know there are a few people in the audience that are interested in connections with constructive mathematics and things like that. So these remarks are that basically those people only. Everyone else can take a break from the lecture. It's not going to take very long. So computability theory can be used to build something called the effective topos, which is a model of intuitionistic mathematics. And it turns out that distinctions like that between not computably enumerable set and productive set correspond to interesting logical distinctions in the effective topos. So one can understand these concepts in terms of set theoretic principles in a certain setting we call the effective topos, which models intuitionistic mathematics. So just to tell you that in the effective topos, so a set A is not computably enumerable. I mean, one needs to be precise or make sense of this, but I won't go into the details here because it's too far away. Not computably enumerable is equivalent to a logical property, which is that for all functions from the natural numbers to A, let's write it in exponent notation. It's not the case that the function is surjective. This is for a set that's an inhabited set A. So being not computably enumerable is like not being a countable set in the sense that there are no surjective functions from the natural numbers. But being productive is the stronger property that says for all functions from the natural numbers to A, there exists an element A in A such that A is not in the image of F. So for those of you who know something about intuitionistic logic, you'll know that saying if there exists something is stronger than saying it's not the case that for all something. So here we've got a not for all statement, well, what's essentially a not for all statement, and here we've got an existing statement. And that distinction is precisely the distinction between the not computably enumerable and the productive. Okay, going back to the lecture, for everybody's ears, let us now give an example of a productive set. And our first example of everything in this part of the course for the last week, for the last few weeks, has been always the halting set K or the complement of the halting set K. So the halting set K will not be a productive set because it is computably enumerable, but the complement of the halting set K is a productive set. So proposition K is productive. Okay. So let's prove this. It's a very short proof. So I've taught this course before. I think on about roughly 50% of the occasions, if I don't use my notes, I get confused in this proof. I'll try and do it without my notes, but we'll see what happens. So, as I say, it's a very short proof. We want to show something's productive. Typically, the easiest way to do it, if you're able to just immediately jump in and find one, is to specify what the outsider finder is, and then prove that it does the job. And the reason that this proof is so easy for the complement of K is that the outsider finder is the identity function. So if we show identity function of the natural numbers is an outsider function. Or complement K. Okay. So we want to show that the complement of K is not productive with the identity function as its outsider function. So we assume that we've got an index E for a computably enumerable set W sub E. It's a subset of the complement of K. And we need to prove then that E, in this case, because that's the identity function applied to E, it belongs to the complement of K that is outside of W of E. Yes, sorry.
Yes, this should be outside the finder, right?
Outside the finder. Yes, thank you. I actually prefer outside the function. That's evolved the literature. Also not literature. That's evolved the terminology as we go along. And outside the function, it's sort of making bringing in shade Um, okay, so that this is an outsider function for k, so the complement of k. So suppose W e, so that's the recursive enumerable that's the complement of k. We need to show our outsider function applied to E belongs to complement of k minus W of B. So our outsider function applied to E is just E. It belongs to the complement. So it belongs to the complement of K. So to prove it belongs to the complement of K, let's suppose it belongs to K and show there's a contradiction there. So suppose, so to show that E belongs to the complement of K, suppose or contradiction K. Now B belongs to K, we have E belongs to K. Remember, K is the set of all those indices E such that the Eth partial recursive function applied to E itself terminates. In other words, such that E is in the domain of the Eth part of the E index partial recursive function. The domain of the E index partial recursive function is exactly W of E. So K is equal to the set E such that E belongs to W of E. Okay, if E belongs to K, then so we have this. So E belongs to W of E. But then because we've assumed that W of E is a subset of the complement of K, we have E belongs to W of E, which is a subset of the complement of K, so E also belongs to the complement of K. But of course, we've got a contradiction because we had here E belongs to K. So E belongs to the complement of K, that's indeed a contradiction. Let me use the slowly double arrow symbol for that. Contradiction. Okay, so we've proved that E indeed belongs to the complement of K. So E indeed. So indeed, E belongs to the complement of K. But the complement of K is simply those E such that E is not a member of W E. And so, in particular, if it belongs to the complement of K, it does not belong to W of E. So E not belong to W of E. In other words, E indeed belongs to the complement of K minus W of E. Indeed, as required, E belongs to the below complement of K minus W of E. Right. Okay, so that's the complement of the halting set. And the main result that I want to prove about productive sets in this part is an extension of the reduction lemma we had when we considered 1 or 2 weeks ago the notion, last week in fact, the notion of total reduction between sets. So recall F total function mutable is a reduction of from A to B, where A and B are both subsets of natural numbers, if for all natural numbers N, we can test if N belongs to A by just testing if N belongs to B. If N belongs to A, it can only affect N to B. Equivalently, the inverse image of B along F is A. And we have a reduction lemma. Which said if A reduces to B, and then we have various properties. We had that if B is computable, then A is computable. We also had if B is computably enumerable, then A is computably enumerable. And turning that last one around, we have, so if B is computably enumerable, A is computably enumerable. So turning that last one around, we have if A is not computably enumerable, then B is not computably enumerable. Okay, that's just the contrapositive of the second part of the reduction lemma from last time. So we're going to add a bis to that, like a bis of the concept. So when you encore, concept, so it's an encore to the reduction lemma from last week. The new third part is we have the second part, if A is not computably enumerable, then B is not computably enumerable. But we're going to strengthen that to if A is not computably enumerable in this strong way, let's be productive, then B is also not computably enumerable in the same strong way. So in other words, if A is productive, then B is productive. So then A productive implies B. And we'll say it's the main result of this part. And in the notes, in the LaTeX notes, it's all in writing. But the lecture I'm going to do it with a picture, but kind of more intuitive with a picture. It'll take a hold of this board. So we can draw a picture of the reduction of A to B. This is the natural numbers here. And reduction is given by function f, the natural numbers to the natural numbers. It's a total computable function. And f reduces A to B. And because we've got a reduction, f reduces A to B, this means, as I said, the condition for reduction is just the same as saying that A is the inverse image of B with the reduction. So the capacity, like, so I will write to the -1 for that, so the standard mathematical notation. So being a reduction is saying that A is the set of all numbers that f maps to B. Okay. Right, let's start a proof in text as well, and we'll sort of go back and forwards between text and the picture as it's convenient for us, I'll just zoom out the camera so the whole board's visible.
Maybe stop the proof here. So suppose A is productive. We want to show that P is productive. And if A is productive, then it has some outsider finder. And so let's write G for that outsider. With outsider finder G. Oh, outsider function, it's now being named. Outsider function G. And what we're going to do is we need to define an outsider function for B. We want to show that B is productive. So we define claim that F composed with G, composed with another function H, which I haven't defined yet, but I'm about to define, is an outsider function D. So where H is defined as follows, so to define H, we're not doing very well with the picture so far, but we are going to use the picture at the moment. So to define H, consider a function that takes a pair of numbers, E and X, and maps them to phi of E applied to F applied to X. We can do this like this, but phi of E, that's the E-index partial computable function. That's, of course, a partial function from the natural numbers. And this function is performing a composite of phi and D composed with F, so this composite function on the number X. And so I did promise you another use of the SMN theorem today, so we now get our use of the SMN theorem. Of course, with the SMN theorem, we can find a computable function H that, when applied to E, will give us the index for this function in its right-hand argument. By the SMN theorem, SMN exists a total computable H numbers such that by H of E applied to X, the point is this H of E gives us an index for this function in its argument X. So this is cleanly equivalent to phi E of F X. What that's saying is that phi H of E is the composite function phi of E goes with that. Okay. So now we've defined H, and we want to show that this f g of H is an outsider function for B. So to prove f composed G composed with H, is an outsider function of B. B. Suppose WE is a subset of B. And we need to prove that phi of G of H of E is contained in B minus WE. We need to show, required to prove RTP that FGHB is contained in an element in B that's outside W of B. So W of B is the E indexed computably enumerable set, which is the domain of phi of E. And we're assuming that that is a subset of B. So here we have, so it's the domain of phi of E. So here we have W sub E, which is some subset of B. So if WE is a subset of B, then its inverse image under F, and here we have F to the minus 1 of WE, is clearly the subset of the inverse image of B. But this, so WE is the domain of phi of E, and this is a total function, and this is the inverse image of the domain of phi of E here. So this is the domain of the composite function phi E composed with F. Okay? And phi E composed with F is as index, is a computable function with index H of E. So this is the domain of phi of H of E, which is W of H of E. So this is W H of E. Okay, so maybe I'll just write that down. Then we have. So what we've seen is then F to the minus 1 W sub E is contained in A, but F to the minus 1 of W of E is, well, that's F to the minus 1 of the domain of phi sub E, because that's the definition of WE, and that's the same as the domain of phi E composed with F, because F is a total function. And that's the same as the domain of phi H of E, by this equality there. And that's the same of the domain of phi of H of E is by definition W of H of E. Okay, so that was the reasoning I did when I was talking to you here. So W of H of E is a subset of A, so because G is an outsider function for A, we have G of H of E is an outsider for W of H of E. So here we have G of H of E. Here, inside A, but outside of W of H of E. And of course, if we apply F to it, it lands in B because it's inside the inverse image of B, but it can't land in W of E because the inverse image of W, because it's outside the inverse image of WB. So if we apply F to it, we get something here, which is in B, but outside W of B. So F, G, H of E is here. So indeed, by the picture, I mean, I could write out the reasoning, but I'm just wondering where that flat pen went. This one here. in H of E, B minus E, because G of H B A minus W of each. And we're done.
Okay, and that has taken us exactly to 3 o'clock. So remember, the thing that slipped my mind earlier when I talked about the outsider function, I was trying to say that there are hints of existentialist literature here, because Albert Camus is now often translated as The Stranger, but his book, The Stranger, was originally translated as The Outsider into English. Anyway, I was going to make some remark along those lines, but it's actually not really important, so let's have a break instead. So it's 3 o'clock, we'll start again at 1:15. Are there any questions? Okay, so good. We'll start again at 1:15. Okay, so productive sets are sets that are not computably enumerable in a strong way. So if we have a productive set, can its complement be computable? A computable set. You can answer that. We have a productive set. Can its complement be a computable set? Yeah. So it can't be, because the complement of any computable set is also computable. So since the productive set is not even computably enumerable, its complement can't be computable. Can the complement of a productive set be computably enumerable? What was our first example of a productive set? Complement of K. What's the complement of the complement of K? K. Is K computably enumerable? Yes. So the complement of a productive set can be computably enumerable. So these are sort of sets that are treading a borderline between computability. There's an interesting situation here. You have something that's half computable on the one side, computably enumerable, but its complement is very strongly not computably enumerable. And so that's thought to be an interesting notion. And so it's given a name. And I really don't understand the terminology in computability theory for this and various concepts that come, but a set that is computably enumerable and its complement is not computably enumerable is called creative. I've no idea why. So, a set A, so the set of natural numbers is creative if it is computably enumerable. Its complement is productive. I suppose one way of thinking about it is that the creative set is a computably enumerable set that fails to be computable in a strong way. Because a computably enumerable set, remember, is computable if and only if it's, so if you've got a computably enumerable set, it's computable if and only if its complement is computably enumerable. So being not computable is equivalent to the complement not being computably enumerable. But here we're saying not just that the complement is not computably enumerable, but it's not computably enumerable in this strong way of being productive. Let's kind of say a computably enumerable set whose complement that fails to be computable in a strong way, that its complement is not just not computably enumerable, but strongly so. Goodness me. Anyway, so that's a creative set, and opposition, nothing to prove. A halting set is creative. And before going on to the main part of this, this middle part of the lecture, as I said, is going to be more narrative based, about telling you about a particular, particularly important productive set. But before doing that, I just want to pick up on Rice's theorem and the Rice-Shapiro theorem that we had last week, and show how these concepts of productive and creative set relate to those theorems. And there are going to be, I think I call them propositions in the notes. Doesn't really matter, but oh no, they're called theorems. So there are going to be two theorems here. I remember Rice's theorem said that if we have a set of unary computable functions that's strictly sandwiched between the empty, so it's non-trivial, it's not empty, and it's not the whole set of computable functions, then its set of indices is never then its index set is never computable. So this is never a decidable set. In fact, we're going to see that in the case that B contains the everywhere undefined function, the index set is not just not computable, but it's productive. So it's not even computably enumerable, and indeed it's productive. So, are we? So, the everywhere undefined function is contained in B, then IB is productive. This means a lot of sets that we describe as the index set of computable functions satisfying some property, as long as the everywhere undefined function is one of the sets that satisfies the property, we get back a set, an index set that's not computably enumerable in a strong way, that is productive. And proof of this, well, we actually don't really need to give any proof, because in the proof of Rice's theorem, so we actually, in the case that in Rice's theorem, we made this without, in the proof, we made this without loss of generality assumption that the everywhere undefined partial function does not belong to B, and then we reduced the halting set K to I of B, and from that we got that it was that I of B was not a computable set. So now we're requiring actually that the everywhere undefined function is in B. So in the proof of Rice's theorem, we in effect reduced the halting set. Hang on. Yeah, we reduced the halting set K to the complement of I of B. It was for the we reduced it to the index set for the complement set, the one that does not contain the empty function. But any reduction of K to the complement of I of B is the same thing as a reduction from the complement of K to I of B. We reduce the complement of K to I of B, and since the complement of K is productive, And we've got a reduction to I of B by the reduction lemma bis that we had just before the break, the main theorem before the break, main lemma before the break, we get that I of B is reductive. So by reduction lemma, this IV is not, sorry, IV is good. And let me see if I can squeeze the last theorem down the bottom. Last theorem is that to do with the Rice-Shapiro theorem. So the Rice-Shapiro theorem, we were looking at those sets B of computable functions, computable partial functions for which the index set is computably enumerable. So those are never of this form, because in this case they're not computably enumerable in a strong way. But for those that are computably enumerable, they're not going to contain the empty partial function, the everywhere undefined partial function. And it turns out that if you have a computable, you have a set of functions that is computed, whose index set is computably enumerable, then that index set is created. That's not really surprising because the index set, we have a set of functions that's computably enumerable. It's not going to contain the empty function, its complement will, and the complement will be productive by this, by what we've just proved here. And so we're going to have a computably enumerable set whose complement is productive. Basically nothing to prove for this, but let me just give the statement. So if the is such that IB is computably enumerable, so such situation was described by the Rice-Shapiro theorem. Incidentally, in the lecture last week, I misspelled Shapiro. I put a C in his surname that shouldn't be there. The correct spelling is in the notes. Anyway, if IB is computably enumerable, then it is created. Okay. So this may seem like some funny concepts, but it's hard to see what they're related to. So actually, I'm going to put that line back. The narrative part now, which is what we're going to go into, is to describe a situation which shows that the notion of productivity gives an example of a situation to which the notion of productivity applies, and which is, I think, most people would agree, a very interesting situation. And this is the set of true statements of what's called the theory of arithmetic, which is the logical statement, true logical statements about the natural numbers, viewed as a set of natural numbers via an encoding. That set is a productive set. And that has consequences. And in fact, one can view it as a very famous theorem in logic called Gödel's first incompleteness theorem, that basically says it's very informally says it's very hard for mathematicians to get their thing to put their finger on the notion of mathematical truth. I mean, we'll say a little bit more about what it says more formally later. And in fact, one way of stating this theorem is to say that the set of truths of the set of truths of arithmetic is productive. So in order to describe that to you, I'm going to tell you there's next semester, some of you may be taking it, there's actually a course on mathematical logic, and we'll do this in more detail and also logic-oriented approach to Gödel's incompleteness theorems. But for
for the purpose of this lecture, I'm going to briefly explain what the language of arithmetic is. It allows us to state, to formally state properties of the natural numbers, and then what it means to talk about the set of truths of such statements, and then the main theorem is that this set of truths is a productive set. And I'll talk about the consequences of that. So we're going to talk about the language of arithmetic. I don't want to get too bogged down formalities here. So I'm going to give a sort of informal description of the formal language of arithmetic, but the point is we're going to have some combinations of symbols that we call formulas, and these formulas are going to state properties of the natural numbers, and then ultimately we're interested in which some of these formulas will be called sentences, and they state properties that are either true or false, and we're going to be interested in which of these sentences are actually true. That's kind of part of the mathematics of number theory, is trying to discover the truths of that. So to speak. The language of arithmetic, we're going to have formulas, and we build and we're going to give ourselves what we call atomic formulas, so there'll be atoms for building formulas. And our atomic formulas are simply, in this case, equalities between equalities between polynomials multivariate, as you can see, we've got n variables here with integer with natural number coefficients. We're just talking about the natural, we're going to have the formal language of the natural numbers, so we're just going to have natural numbers. Natural number and the notation here, I mean, we know how to write polynomials with natural number coefficients. We've got multivariate polynomials, so we're allowed to multiply different variables with each other and with themselves to raise them to powers. The x1 to xn means we're using up to n variables on the left-hand side and up to n variables on the right-hand side. We don't need to use all the n variables on either side. Also, n could be 0. So special cases of this include univariate polynomials, those that only have one variable, and an even more degenerate case in which you don't have any variables at all, and then the polynomial will simply be a constant. Which is okay, so this includes statements of equalities between natural numbers, or even x equals 3, or statements like that. But the general form of atomic formulas today is this: when one does logic, one reduces it to simpler things. That's enough for us. Then, if we have formulas, we can close them under the once we have the atomic formulas, we close them under the usual Boolean connectors, which is propositional logic. So if phi and psi are already formulas, then there are, well, we can form not phi, phi and psi, phi or psi, phi and phi psi. I mean, so, but that's enough. And in fact, just negation and conjunction would have been enough. Think about classical logic, which we are. And the other thing we give ourselves are the quantifiers, the universal quantifier and the existential quantifier. So phi is a formula we've already built up, and so the formula for all x phi, where we're talking about theorem of arithmetic, so we understand our quantifier for all x as stating the property for all natural numbers x phi is true. and exists in this one. Exists in that number. And that's it. So it's very, very simple language. But in that simple language, one can already express quite a lot of things. So, for example, I kind of always give the same examples when I present logic at this kind of level. So, for example, we have the formula, there exists a natural number z such that x plus z equals y. So that's stating a relationship between x and y, which hopefully somebody can immediately see what it is. What's the relationship between x and y? So natural numbers include 0. So, so this is this expresses x is less than or equal to y. Then oh well, never mind. I'll just show that on the video while I'm cleaning the other board. Actually, we can do one more example down here. So another property would be so now we can say x is less than or equal to y, but using a formula like this. So we can use this as a shorthand. So we could say that x is, well, this is a 2. So 2 is less than or equal to x, and for all y for all z, if x equals y times z, then x equals y or x equals z. Okay, yes.
A question about syntax. Which basic function symbols do we have in this language, the language of arithmetic?
Because I'm not doing it so formally in talking about basic function symbols. I'm saying we can have equalities between multivariate polynomials. Y times z is a multivariate polynomial. So is x, and this is an equality between multivariate polynomials. But one can perfectly well encode this by just having addition and multiplication as the two functions. Anyway, so what does this say? It either says x is prime or I've written the wrong formula. It's supposed to say x is prime. So this expresses x is prime. So we can abbreviate this as prime x, the property of x being prime. And then we can state things like, let's go to, now move the camera. Oops. And what about this? For all x, there exists a y such that x is less than or equal to y, and let's use prime. So less than equals is just the shorthand for what we wrote here,
and prime of, I'm now going to say prime of y, but you can sort of change this to say y is prime. And so you basically formulate that in the way that we had before, and prime of y. So what does this state?
There are infinitely many times.
Yeah, so this is, there are infinitely many prime numbers. And just one more example. So for all x, there exists a y such that x is less than or equal to y, and prime y, and prime y plus 2, which one can formulate using this language. With use this formula for y plus for the y plus 2 is again a multivariate polynomial, and you can this is with this language. So what does this state? What's called the very famous conjecture in number theory called the twin prime conjecture, that there are infinitely many primes 2 apart, and this is not known. There is some, in the last 10 years, some bound was proven that there are infinitely many primes, some fixed number bound apart. So that was a major progress in number theory about 10 years ago. But anyway, this result, this long been conjecture, but is not known to be true. Okay, we notice, I mean, many of you will know enough about logic to know all this already, but we noticed that this first example of less than equals was expressing a relation between two numbers, x and y. The second example being a prime, is expressing a property of a single variable x being a prime. And these two statements here, these two formulas, express properties that are either true or false. In the first case, it states there are infinitely many primes, which we know to be true. We've known that since time of Euclid. And in the second case, that there are infinitely many twin primes, as they're called, which is either true or false, but at present nobody knows which one it is. The point I want to make is that there's actually a syntactic distinction that distinguishes between the properties on the right-hand board here and the properties on the left-hand board, where the ones on the left-hand board are properties that are either true or false, and the other ones are basically relationships between numbers or properties of a variable. And that distinction is that, so in this formula, x and y are variables that are not within the scope of any quantifier. And similarly, in this formula for being a prime, x is a variable that's not within the scope, not within the scope of a quantifier quantifying over that variable. Similarly, x is not a quantified variable here, whereas in these two formulas, all the variables are quantified. And we say a formula is a sentence if all the variables are quantified, if all its variables are quantified. Another way of saying it is a concept of free variable if the formula has no free variable. A formula is a sentence if all its variables are quantified. The point is a sentence states a property that is either true or false. But it may be an interesting question to prove that it's true, like there are infinitely many primes. I mean, it's one of the first examples one learns of a nice mathematical proof. It's still nonetheless a nice mathematical proof. Or it may be a question that's very hard to prove, but we still have a proof for. Or it may be a question like this, the twin prime conjecture, that's so challenging that in all the millennia of mathematics, nobody has so far managed to prove it. But the point is, a sentence, every sentence, if one is classically minded, every sentence expresses a property that is either true or false. goal of mathematics, the goal of important goal of mathematics is to discover which sentences are true, and is find interesting examples of sentences that are true. So one of the points of doing things with formal logic is you have a precise language for stating properties of mathematical properties, and this precise language can be given precise rules for reasoning, and because it's a precise language, you can also use this language on a computer to write properties of mathematics. And because we have the precise rules of reasoning, we can also implement the rules of reasoning on a computer. This leads to technology such as things called proof assistants that allow you to write interactively proofs with the proof assistant checking your proof as you write it and making sure you don't make any mistakes. And in the end, you hope to get to the end of your proof, and the proof assistant will say, yes, that's a correct proof of the result that you're claiming. And also other technology called theorem provers, where a theorem prover, the ideal theorem prover, which doesn't exist yet, but the ideal theorem prover is you would put the statement in that you want to be proved as an input. The theorem prover would go away and apply its clever algorithm, and at the end it would come back out saying, here's a proof of your statement, or here's a disproof of it, or something like that. Yes?
Didn't Church prove that such a perfect algorithm doesn't exist, or similar to the businesses we get?
Yeah, there is no perfect algorithm, and this is kind of where we're going to go to as well. But still, there is actual real-world technology that behaves in much this manner, although the proof assistants are quite well developed, the theorem provers much less so. But yeah, still, it's exciting technology that people are working on. So, yeah, one's interested in having this formal language so one can, for example, interact with computer technology to help one do mathematics and have one's theorems checked. And this technology is applying algorithms that are dealing with formulas and essentially verifying things like, is this proof that I have dealing with these formulas, is this proof correct? Or simply, one might even think it would be, if one were really naive and we kind of rolled back 100 years or so, went to what people knew about then, you might even hope that the best thing one could hope for from a computer is, even ignoring the concept of proof, you type in your formula, the computer goes away and thinks for a bit, and it comes back and it tells you it's either true or it's false. That would be really cool if such a thing could exist. So I'm going to give you a result that says that no such thing exists, but it will actually tell us much more than that, which I'll talk about afterwards. But to get the result, we need to translate the formulas into natural numbers. We need to encode the formulas as natural numbers because at the moment, the computability theory we've developed for the last few weeks, including today, has been about properties of natural numbers. But that's easy now. We've seen how to code lots of things as natural numbers. So it is not hard to encode formulas as numbers. And a nice encoding will enjoy the properties like if you have two different formulas, then they're encoded as different natural numbers. And if you have a natural number that encodes a formula, you'll be able to algorithmically extract the structure of the formula from those natural numbers. It will be able to tell you whether it starts with a universal quantifier or an existential quantifier or a conjunction or what have you. So we can do that. One way to see that we can do that is the formula as defined is simply a sequence of symbols. So it's like a word over a sufficiently rich alphabet, and then we know how to encode words of words over alphabets as numbers. Actually, a better way to encode things is to respect the structure of formulas a bit better and to encode them as what's it called, abstract syntax trees. It doesn't really matter. There are many ways of doing it, and one can encode formulas as numbers. Moreover, we can encode it in such a way that the set, we then have a set, which we might call form, which is simply defined to be a set of those numbers. So now phi means a formula, and this means the encoding of phi, so phi is a form. So this is just the set of all numbers that encode formulas. And if you encode formulas in a sensible way, this set is perfectly decidable. You can take your number and you can check whether or not it interprets. I mean, it's even possible to make the encoding a bijection with the natural numbers if you want to. But it's anyway. However, if you do it the encoding in any sensible way, you can decide whether a natural number is an encoding of form. So form is a computable subset of numbers. And then there are those, we're really interested in those formulas that express properties that are either true or false. Those are the sentences. So we have a subset of form, which is by the encoding of those formulas that are sensible. So those in which all variables are quantified. And again, sentence, set of numbers encoding sentences is again computable. You basically look at your encoding of a formula, and then you extract the structure of the formula, you go through it and you check that all the variables are inside quantifiers that name it. So send is again computable. But then we have kind of what should be the most interesting set of sentences, which we'll call true. We don't need to worry about any axioms or anything at this point. We just we have a formal language. It's clear what properties they're all expressing, and most people would see those definitions and agree that any sentence defined in this way, where you've only got quantifications over natural numbers, is either objectively true or objectively false as a property of all natural numbers. The true is the sentence is the coding of all phi's where phi is a sentence, and it's true. By the way, just out of interest, how many people in this audience believe that every formula defined in this way has an objective truth value?
In what sense?
That doesn't sound like a true question.
It's not a trick question, but
This is about mathematical statements.
it's about your mathematical belief. I mean, when in mathematics you have the whole structure of sets or types or whatever you use, but that includes you have natural numbers and power sets of natural numbers and the power set of natural numbers, and then lots of much bigger things, and things get really hairy. But here, all we're talking about is natural numbers, and we're simply doing a finite number of quantifications over natural numbers. It's not. So something like the twin prime statement is a for all existence statement, but most people would agree that even though we don't know that it's, we've not been able to prove it, and maybe it's even false, it does have an objective truth value.
We could still have some statements that were independent from our arithmetic.
Yeah, but this is independently of axioms, just to do with the meaning. We're not got any axioms at this point. I mean, I'm not axiomatizing anything.
So just like
Yeah,
objective, even above axiomatization.
yeah, certainly about axioms. So just. So how many people believe there's an objective truth there? Okay, a few more. I've done a bit of a cell. How many people doubt it? Wow, we've got some skeptical people there. Okay.
So the question is whether it's not unprovable when you also have some objective platonic truth.
Well, so this is independently of axioms. So there's no, even before the notion of proof, it's just, simply imagine yourself checking whether a sentence is true, which you can perfectly well do if you give yourself infinite time to do it. So, yeah.
Yeah, put the notion of independence a bit more precisely, I guess that I imagine this as phi always has like a it has semantic truth in a certain model theoretic setting, and independence means that in a certain theory, phi is neither provable nor disprovable. So phi is not
So by
provable.
dependency meaning completeness.
Yeah. So
Yeah.
are we talking about?
Well, we haven't got to incompleteness yet, but I was just trying to say these are very simple properties that we're stating, where you've just got a finite number of quantifications over natural numbers, and then something on the inside that's essentially checking a bunch of polynomial equalities. And anyway, personally, I believe such things have an objective truth value. If you don't believe that, then you have problems understanding this set definition, and I apologize for those problems. But one doesn't have to believe that much. One doesn't have to believe in some sort of very terribly complicated Platonic universe to believe that this notion of truth is defined. Anyway, so the main result about this is that true is productive. What does this mean? Well, it says if we have any computably enumerable subset of true, then, well, it is more than that. We have a computable function that, given an index for a computably enumerable subset of true sentences, will find a true sentence that is not in that computably enumerable subset. Okay? And the way this then relates to, and people have been talking about axiomatizations and things like this, what this tells us is that we can never completely axiomatize the truths of arithmetic. And that is Gödel's first incompleteness theorem, which his way of stating it is more logical. But we can understand it in this sense. If we have an axiomatization we can write down, or any axiomatization we can write down that we think of as an axiomatization for the truths of arithmetic, that will give us a way of generating truths, namely all the truths we can produce from the axioms. There are certain reasoning principles one can use for generating theorems from axioms, and those reasoning principles are perfectly computable in such a way that if you've got a set of axioms, you can generate one by one all the set of all consequences of all those sentences that are provable from your axioms. Okay, all different ways of combining. You just go sort of systematically through all the different ways of combining the methods of reasoning from your axioms, and you'll generate all the set of all consequences from your axioms as you can enumerate through it. That says the got an axiomatization, the set of consequences of your axioms is going to be a computably enumerable set. And if your axioms are sound with respect to, you're trying to axiomatize truths, but if your axioms do indeed just consist of true sentences, then we're going to get a computably enumerable subset of the truth. We can then take the description of our axiom of this procedure that gives us the computably enumerable set of or consequence of the axioms, apply our outsider finder, our outsider function to it, and that outsider function is a computable function that will give us back a new sentence that's a true sentence, guaranteed to be one that we can't prove from the axiom. And this productivity is saying for any axiomatization, we can computably, from a description of the axioms, find a true sentence that is not provable from those axioms. So then you might add that as another axiom. You've then got a different description of your, now got a larger set of axioms, got a different description of axioms. You've managed to incorporate the true sentence you didn't have before, because you've now added it to your axiomatization. However, you can apply the outsider finder again to your new axiomatization, and you'll get a new truth you didn't consider before. And you can never escape from this situation. Whatever truth you axiomatize, you can always computably find a new one that you can't prove from your given axioms. So that is the computability theoretic version of Gödel's first incompleteness theorem. You don't need to know much logic to understand this statement. You do need to know some logic to understand the proof. In the notes, and this is not, it's not examinable, this proof, this argument, but in the notes there's a high-level argument for why this theorem is true. But what I hope, the main thing I wanted to convince you with it is that it's an example in which the notion of productivity is really telling us something interesting to say. Okay. 2 minutes past 4, sorry. Okay, that was your phone. Yeah, so, anyway, it's 2 minutes past 4, so we'll start again at 17. Any questions? Yes? Sorry? So an axiomatization is a set of axioms that we decide are the basic truth.
Yeah, I think.
It doesn't need to be finite, it just needs to have a finite description. Take the logic course next semester. Yeah, okay. Sorry, let me just pause the. Okay, so as I said at the start, the last part is going to again be a technical part, and we're going to stay on the subject today of varieties of non-computable sets. So we've already seen set. We've already seen two kinds of non-computable set today, or not even computably enumerable sets. Well, actually, no, one of them was. So we've seen productive and creative. And we're going to see, so these ones, the creative were computably enumerable, but their complement was productive. So we're going to see two new kinds of non-computable set called, this is so far, in this part we're going to see two new kinds of non-computable set, the immune sets, and lastly the simple sets. And since this is the third lecture in the core computability theory that's steadily getting more and more technical, you might imagine that simple is an oxymoron. Yeah, you know what that means, a contradiction in terms. So the simple sets are anything but simple. I've got no idea. I mean, maybe that was the joke when people named them. I don't really know where these names come from. But to get there, we're going to stay with productive sets for the moment and just observe a last interesting property of productive sets, and that's a theorem. Oops, and that's not a good pen.
So the productive set is a set that's not computably enumerable in a strong way. Any productive set is, of course, infinite, because every finite set is not just computably enumerable, it's computable. So a productive set is necessarily infinite. And this result is going to say that every productive set has an infinite computably enumerable subset. So the productive set is not itself computably enumerable, but at least it contains an infinite computably enumerable subset. You may remember a couple of lectures ago we had the result that every infinite computably enumerable set has an infinite computable subset. So that also means that every productive set has, combined with this, every productive set has an infinite computable subset. We just prove, we don't need to prove the second part there, we just prove that it's enumerable subset. So proof, the idea is simple enough. So suppose A is productive with outsider function G, and we're simply going to construct a specific, we've got a very methodical way of finding an infinite subset of A, which is as follows. We're going to define a total computable function. A computable total function f from n to n, satisfying that when we apply f to 0, we get some index which we'll call E0, which is, well, where E0 is some code for some index for the everywhere undefined function. So that means if the everywhere undefined function, that means W sub E0, the domain of the function it encodes is the empty set. And once we've got E0, we can then, we'll then use that to get f of 1. This is going to be E1, such that W E1, so the domain of E1 is the code for a computable partial function that is defined on exactly one element of A, and that element of A is G of E0. So notice that G is our outsider function, so if we apply G to E0, E0 represents, is the index for the empty computably enumerable set, which is of course the subset of A. So our outsider finder function will find an element of A which is outside the empty set, which is harder to be outside the empty set. So G of E0 is an element of A. And now we form a new set. This and this is going to be the domain of our E1. Once we've got this E1, then we can find F2, it's E2, such that, and basically what we do is we keep on, we're making finite, we're constructing a sequence of finite computably enumerable, well in fact computable because they're all finite, computable subsets of A, using, for each previous one, we use the outsider function on its index to find a new element and to put it in. And here it will keep G of E0, we throw in the new element G of E1. We'll just do one more step. F3 is E3 such that. So once again, we we apply G to E2, that will give us an element of A that's outside this set. So we then get to 3 element set. If we add it, so G for E0, G for E1, G for E2. And so. And once we've defined such a computable function, so then we have the G composed with F. So G of E0 is giving us this element, G of E1 is giving us this element, G of E2 is giving us this element, and so on. So we get an infinite sequence of elements of A, all of which are distinct. So each new one is guaranteed not to be in the previous set. So G of F is a total computable function whose image or range is an infinite subset. A. And because we had a couple of lectures ago that the images of total computable functions are computably enumerable sets, so its image is an infinite computable. Its image is therefore infinite CE subset. And really that's not quite the end of the proof, because I haven't told you how to define F. I mean, I've told you we want an F doing this, but we need to be able to see that we can actually write such an F in a computable way. So this is examinable for the theory exam. It's very short, but I think I'm going to skip it from lecture. It's in the notes. It's a good exercise for you to do your exam. It seems to me, it doesn't feel like the most exciting thing to do right now. So, the way we're going to take this is what we're going to show is that there exist computably enumerable sets that don't have, there exist infinite sets that don't have any infinite computably enumerable subsets. And such an infinite set is, of course, not computably enumerable, because if it were computably enumerable, it would be an infinite computably enumerable subset itself. And because it doesn't satisfy this property, it's an example of a set that's not computably enumerable in a way that's not being productive. So we've now got a separation of two different kinds of interesting sets that are not computably enumerable. Those that are productive and those that have this other property, and this property is being immune. Okay? Again, I don't know why it's immune, but anyway, that's the terminology. So a set A numbers is immune if it is infinite and it has no infinite C subset. We have immediately, if A is immune, it is not CE, and also
if A is immune, it is not productive. Because of this theorem of productive set. Okay, and the main remaining thing to do in the lecture is to prove that an immune set exists. I'm going to do something a bit stronger than this. So again, this is another, if you like, strong way of not being computably enumerable. So that gives us another complementary property, which is a strong way that a computably enumerable set cannot be computable. Namely, the first strong way a computably enumerable set might not be computable is if its complement is productive. And that gave us the notion of creative. The second way now, we've got another strong way of not being computably enumerable. So the second strong way a computably enumerable set might not be computable is that its complement is immune. And that's what a simple set is. So a set A of natural numbers is simple if it is computably enumerable and its complement So I wanted to prove there's an immune set, but I'll do something stronger than that. I'll prove that there exists a simple set, and then, of course, its complement is an immune set, but we have an immune set whose complement is immutable. So it's stronger property. So maybe before doing that, it's time to just make another side remark for people that are interested in intuitionistic mathematics, because immune sets, again, in the effective topos, so this is just for people that are interested in sort of side remarks related to higher things, so to speak. So relationship to constructive mathematics. Again, this is absolutely not examinable material. So again, in the effective topos, immune set numbers corresponds to a set, a set that enjoys the logical properties A is infinite, meaning there exists an injective function from every finite set into A, and all F from all functions from the natural numbers to A, the image of F is finite. So it corresponds to infinite sets for which there does not exist any way of enumerating any infinite subset of the element. So such a thing would be kind of quite weird. Anyway, so So I guess the point is, the world of intuitionistic mathematics can be quite weird. That weirdness, so this is an example of such weirdness, but that weirdness is reflected by the weirdness of computability theory. Or is mirrored by the weirdness of computability theory, in the sense that computability theory actually tells us what the weird properties can be. Use that to find examples. Logical properties like this is very strange, but are actually consistent with intuitionistic mathematics. And by the way, I didn't prepare this carefully before saying it. So actually, as I wrote this down, I sort of had a little bit. I had about 3 different versions that I wanted to write all at the same time, and I should have really thought carefully for which one was precisely right. It looks like it's plausibly okay, but if it's not exactly this, it's something very similar.
It doesn't matter because it's not examinable material. The other thing is, it's also off the video, because once again, I forgot to. So I'm sorry for people watching the video. Maybe I'll scan that over, and somebody may tell me that this was wrong, what I said, because I didn't think it through properly. But what we want to do now is construct a simple set. This is theorem is a name. Post's theorem. It's not Post's only theorem. Anyway, it's a good one. It's not particularly hard, but it involves a little bit of a cunning construction. So Post's theorem exists for a simple set. This one I can't agree with that notes. So we're going to consider a partial function f. Defined as follows. So f defines an index of the computable partial function e to, we've got 2 cases. We return phi e of z if we can find z, which is the smallest number such that phi e of 0, phi e of 1, such that phi of e is defined on all arguments up to and including z. So these are all defined. And phi e of z is sufficiently large, which means it's greater than or equal to double the index. Okay. And if we can't find such a z, then this is undefined. This is computable because we've got the universal function psi universal, but we can use e as the first argument and z as the second argument. And we simply search from 0, 1, 2, 3, and so on in parallel, waiting until we get an initial block on which all the parallel executions, phi of 0, phi of 1, and so on, all halt. And the last one is greater than or equal to 2 times v. At the point that we found that, we checked the previous ones as well, and we returned the first one that's greater than or equal to 2 times v.
And what was one after the other, if the first one.
Oh, yeah, absolutely, very good. We can in this case, because they all need to be defined. No, that's much better. In fact, much simpler, run the first one, wait till you get an answer. If it's greater than or equal to 2e, you're done. Otherwise, run the second one, wait till you get an answer. And the first time, you're only going to then get an answer if they've all halted before. And when you get one, as soon as you get one greater than or equal to 2e, then you get much better, thank you. Okay. And we define, so that's a computable function. That's by that argument. And because it's computable, its range is computably enumerable. The range of a computable partial function from a few lectures ago is always computably enumerable. So define A equals the range of F. So then A is CE, clearly. It's the range of computable partial function. We're going to prove that A is simple. So that means we need to show that the complement of A is infinite and that the complement of A does not contain any infinite computably enumerable sets. So maybe we'll go into this part of the board here. So to show complement of A is infinite, so notice when f of v is some number n, we always have that n is greater than or equal to 2 times v. So when f of v equals n, we have n is greater than or equal to 2 times v. So f of 0 is greater than or equal to 0. F of 1 is greater than or equal to 2. F of 2 is greater than or equal to 4. If it might not be defined, but if it's defined as greater than or equal to 4, f of 3 is greater than or equal to 6, and so on. And you see that we're using up numbers at only at half the rate that they're coming to us in the argument. So up to, say, f of 15, but f of 15 will be greater than or equal to 30, but to get the number greater than or equal to 30, we've used in the first place a number greater than or equal to 0, then a number greater than or equal to 2, a number greater than or equal to 4, a number greater than or equal to 6, and so on. Each time, we've left at least half the numbers unused. So how to write that formally? Well, what I've got in the notes is, so the numbers 0, 1, so on up to 2, n minus 1. And here it only appear that these values can only be taken as values for f of v, as values f of v when e is less than or equal to n. So when e is less than, when e is strictly less than n. Okay. So that means for every n equals 0, So we can only use n of these numbers for the, we can only use n of these two n numbers. So at most n. So for every n greater than or equal to 0, at least 10 distinct numbers from this set between 0 to n minus 1 belong to the complement, do not appear in the image of that, so they belong to the complement of that. And that's true for every n, so therefore n is infinite. Sorry, so the complement of n is infinite. Okay, and so now we need to show, so it only remains to show that the complement of A does not contain an infinite computably enumerable subset. To show that the complement of A does not contain an infinite computably enumerable subset, let's let B be an infinite computably enumerable set, an infinite C set. And we need to show that this is not a subset of complement of A. So we show that B is not a subset of complement of A. So since B is an infinitely computably enumerable set, we had a couple of lectures ago that every infinite computably enumerable set is the image of a total computable function. So that's true for non-empty computably enumerable set. Since B is CE, it is some result from 2 lectures ago. We have the range, the image, phi of E for some total phi of E. But in that case, if phi of E is total, then f of E is defined because B is the range, but B is infinite, and therefore there must exist some element of B that's greater than or equal to 2 of E, to 2 times E, and because we just take the smallest. We just take the smallest such value z, such that we want there exists some z such that phi of z is greater than or equal to 2 times E because its range is infinite, and we take the smallest such z, and because it's total, all these previous values will also be defined. So how do we write that? So since B is infinite, there exists Z such that phi of Z needs to be greater than or equal to 2E. And then f of E equals the smallest subset. So this smallest subset D equals phi of Z equals phi E of Z, or the smallest subset. So this by E Z belongs to B. Sorry, belongs to A because A is the range of F. And hence and belongs to B because C is the so this belongs to A intersect B. A is the range by E, and therefore we show that B is not a subset of the Hamilton. So we indeed have a simple set, and therefore its complement is an immune set. So simple sets and immune sets exist. Now, whereas in productive sets, I gave you lots of natural examples of productive sets, and then there is this middle part narrative arguing that also productive is sort of relevant to clearly interesting concerns like the notion of truth, mathematical truth, at least pertaining to number theory. Here we're in the opposite situation that to construct a simple set, we had to do something quite convoluted. It's so it's this question: are there naturally occurring simple sets? So yes, that's something. Actually, I was just raising that question. I don't think I've often seen naturally occurring examples of simple sets, but nonetheless, it's a kind of curious little phenomenon, and I think an appropriate little phenomenon to end this part of the lecture course on core computability theory. As I said, next week we're going back to basics, we're going back to Turing machines. As I said at the start, but a new type of Turing machine, the so-called type 2 Turing machines. So yeah, so that's it for the main core part of the course. Any questions? Okay. Well,
What should the lectures after New Year's? Because you told us what's the plan.
aha, the lectures after New Year. There are 2 lectures after New Year, and I haven't decided what I'm going to do yet. So yeah, I shall think about it over Christmas and the New Year. See what feels right.
Give us something. This is sort of a theorem. Sense. Historically, they first define a simple set, and then they look for that there is one, and then we'll show the existence thereof. Right? And my question is, I guess, why did they define this notion without it being, without it being a very good example?
So I'm not really sure of the history here. I doubt it was an open question. I think probably Post is trying to show that there are examples of non-computably enumerable sets that are not productive. I guess that was, and this is a good way of showing that. Probably it was that. Only I may be forgetting something. Okay, good. Okay, I'm going to stop the video and